Okay, so now Laszlo Babai will continue his talk on symmetry and regularity.
Okay, so this is going to be now another round of inferences from regularity. So we are assuming now regularity on the structure, and we want to prove consequences that normally are consequences of symmetry assumptions, but we want to derive them from regularity. Okay, so okay, here are some examples of strongly regular graphs. First of all, the trivial ones are just unions of disjoint cliques and the complements of this. The complement of a strongly regular graph is also strongly regular. Maybe I should recall what is a strongly regular graph. It is a graph which is regular, so every vertex has the same degree, so same number of neighbors. And for a pair of vertices, the number of common neighbors of that pair only depends on whether or not the pair is adjacent. That's what is called strongly regular. And so, for instance, Peterson's graph or the pentagon, these are examples of strongly regular graphs. Okay, the trivial strongly regular graphs are if I take disjoint cliques of the same size, so a clique is just a complete graph where everything is adjacent to everything, that's clearly strongly regular. It's a trivial one. It has lots of automorphisms. It's at least, square root of n factorial squared or something. So it's exponential in square root of n if I ignore log factors. Okay? Now the Hamming graph which has this parameter 2, so this means I'm looking at words of length 2, just 2 letters in the alphabet. So it has k squared vertices. You can think of it as the k by k chessboard, and 2 vertices are adjacent if they are on one line for the rook. So this is the graph of the rook on the chessboard. Okay, so that graph clearly has twice k factorial squared automorphisms. We can permute the rows, we can permute the columns, and we can swap the rows against the columns. So this is essentially n to the square root of n. N is the number of vertices. Okay, now the Johnson graph also with parameter 2. So this is all 2 subsets of a k set. So it's k choose 2. It's the line graph of the complete graph. We look at the complete graph. The edges become vertices, and adjacency represents intersection. So that has k factorial automorphisms, which is still essentially n to the square root of n. I ignore constants. I even ignore logarithmic factors in the exponent. But that's the point. This grows moderately exponentially, not even so moderate. The exponent is square root of the number of vertices. And this list I am going to call the standard exceptions. Standard exceptions from what? From much better upper bounds on the number of automorphisms. So these are cases where the number of automorphisms is large, and then I am curious how large it can get for other than these. Okay? So here is the conjecture that I have been proposing for a long time, that the automorphism group of a strongly regular graph is quasi-polynomially bounded unless it is one of the standard exceptions. In standard exceptions is exponential, but for all others, this is. The best that is known is a rather mysterious upper bound, n to the 937ths in the exponent by Shi Chen, Xiaorui Sun, and Xianghua Teng. From just a few years ago, this result was motivated by the graph isomorphism problem, but soon we superseded that and then further. However, this aspect of the result, that it gives a bound on the order of the automorphism group, this survives, and this is the best, and we tried to improve it. It's not clear how one could improve it. There are 2 possibilities here. Either this conjecture is true, in which case it would be a fascinating result. But if it is false, the falsity would be proved by some very interesting, not yet known strongly regular graphs. So that would be an interesting type of construction that I would also like to see. So yeah, either outcome would be interesting. All right, so we want to bound automorphisms. Certainly irregularity helps. Irregularity helps refute isomorphism, and it also helps keep a check on the number of automorphisms. Now, if we get a graph where we don't see any obvious irregularity, then one thing we can do is we can create irregularity by individualizing a vertex. So we just put a special color on that vertex, and now the number of automorphisms actually has been reduced by a factor of 10, because there are 10 vertices. So, and then I can refine this. Okay, so this is now the neighbors of this vertex are going to notice, oh, I am a neighbor of a little red star, so I call myself green. But then it doesn't go any further. So this is basically splitting the graph into 3 types of vertices: the little star, the green vertices, and the rest is still more than half. So I'm not happy with this effect yet. I individualize a second vertex. And after doing the propagation, so everything notices the colors and multiplicities of colors in their neighbors repeatedly until it stabilizes, then we notice that finally it stabilizes at a point where every color occurs at most twice. So I split up the entire set into color classes that are small enough, and maybe I can say that, all right, I made sufficient progress here on either problem. So the problems I keep in mind are 2 very closely related problems. One is determining whether or not 2 graphs are isomorphic. This is an algorithmic problem, or simply theoretical estimates on the order of the automorphism group. Either of these problems, this is a methodology for both. And actually, these are the methodologies that have been the only ones that have been successful so far in bounding the number of automorphisms of all those objects that I listed. So this is an old heuristic, of course, the most natural heuristic in graph isomorphism that every chemist who was ever interested in comparing organic molecules has also invented, and that goes back to at least 4 decades. But analyzing it is a different question. Okay, so in any case, this refinement was achieved by individualizing 2 vertices. And individualization incurs a cost. Even if we just individualize 1 vertex, then we look at an automorphism. So here is another copy of this graph. This could go here, or it could go here, or here, or here, or here. I can't tell you how much it took me to produce this 3-second animation. But anyway, so clearly irregularity helps, but it comes at a multiplicative cost. We are going to branch. Okay, so our problem of looking at what are all the automorphisms or what are all the isomorphisms, they are going to branch as many ways, essentially n to the t ways if we individualize t vertices, because we have to match those t vertices with any t tuple of vertices. So this branching factor, this is the number of instances in a canonical set. Okay, so if I individualize the vertex, then the new graph, which has this irregularity now, is not canonical with respect to the original graph. So if I can have isomorphisms between graphs where the individualized graphs are no longer going to be isomorphic. The set that is canonical is all individualization. So I individualize vertex number 1 or vertex number 2 or vertex number 3. This collection of graphs is now canonical. And so the branching factor is the size of the canonical set. I reduced my original problem to something that is presumably more tractable because it is less regular, but there is a price to it, and this is the price to pay, the branching factor. Okay? All right. I described the naive refinement where a vertex just looks at the color of the neighbors and how many neighbors have a given color, etc. More advanced refinement was already published in 1968 by Weisfeiler-Leman. Now, this is contemporaneous with even the rise of the notion of polynomial time. So what they do is simply they color all pairs of vertices. And then they do the natural refinement. If I have a pair of vertices and it has some color, then into this color I also encode the number of vertices which are connected to one of them with one, say red, and with the other with green. So I pick 3 colors, blue, red, and green. And I look at a pair of vertices that are connected by a blue edge, and then I look at the red-green walks of 2 steps that take me from the tail of this edge to the head of this edge. This is now a directed graph. And I encode it into the new color of this edge. So now, if this parameter was different from 2 blue edges, then one of them is going to become light blue, the other is becoming navy, and so these are no longer going to be the same color. So this is how we refine the coloring. The refinement always encodes the previous color, so it is refinement, but it encodes a lot more information. So this procedure, in every round, I look at these numbers, I get a new coloring, and then I do it again until it stabilizes, so until we get no more refinement. So clearly this happens in polynomial time, and, and the stable configurations under this Weisfeiler-Leman canonical refinement are called coherent configurations. So configuration is coherent if the number of red-green paths of length 2 from the tail to the head of an arrow is determined by the color of that arrow. Okay? That's the definition of a coherent configuration. So that's a strong regularity condition, and we can always achieve it. And moreover, this process is canonical. This doesn't change isomorphisms. If I had two graphs or colored graphs already, so I am in the middle of the process, and I had an isomorphism between them, that isomorphism is preserved. So in particular, also the order of the automorphism group is preserved. This also says, by the way, that this refinement process leads to a type of object of which to decide isomorphism is equivalent to deciding the isomorphism of the original object. So we express this by the term coherent configurations are isomorphism complete. So the isomorphism of graphs can trivially be reduced to the isomorphism problem of coherent configurations. Okay, now, so a little more word about the individualization and refinement heuristics. In lucky cases, this would lead to a complete split. In the example I showed you, it didn't lead to a complete split because there were still pairs of points that had the same color. A complete split would mean that every vertex has its own individual color, not shared by any other vertex. If individualizing t points can result in a complete split, then obviously the automorphism group is not greater than n to that number. N is the number of vertices. Because this just means that we individualize t vertices. We just have to look at how we can map those t vertices into the other graph, or the same graph if we look at automorphisms. And every such mapping has at most one extension to an automorphism or to an isomorphism. Okay, so let's go back to coherent configuration. So here is the definition of a coherent configuration. We take a set of vertices V, and then we partition V cross V. Now, it is required that diagonal colors and off-diagonal colors are different, so the vertices get colors, and the pairs of vertices that are distinct also get colors, and it is required that the color of x to y determines its reverse. Okay, so if I look at one of these relations, any one of these relations is either a symmetric relation or its inverse is also one of the relations. And finally, there are these so-called intersection numbers that describe how many neighbors of a given color, how many paths of length 2 of a given color composition go from the tail to the head of an edge of a given color. So this has three parameters, I, J, and K. These are three colors. I take like these three colors that we see in the picture, and then I count the number of, say, red, green paths of length 2 from the tail to the head of a blue edge. This number is determined by the three colors I mentioned and doesn't depend on the particular choice of the vertices x and y. Okay? So these are called intersection numbers. There is an associated algebra, an algebra that is associated with this, namely the algebra generated by the adjacency matrices of these directed graphs that are the individual colors, and these are the structure constants of that algebra. Okay, so here is an example. The rank of the configuration is the number of colors in the configuration. So in this case, it is 7. That includes red and blue, which are the colors in the diagonal. And then there are the off-diagonal colors. There are 5 more colors there. And some of the colors don't have arrow on it. And what I denote by that is that it is a symmetric relation. Okay, so the color from A1 to A3 is the same as the color from A3 to A1. However, the color from B3 to B1 is not the same color, but I didn't particularly want to mess up the picture by drawing a reverse color in a different, by a different color. Okay? All right. So all the colors are like the inverse of purple, the inverse of green. There are separate colors. So this is a coherent configuration. This coherent configuration is related to a permutation group. If you look at this permutation group where to these 3 points, the 3 red points, I apply the symmetric group of degree 3, and to the blue points, I apply the cyclic group of order 3, and I take the direct product of these two groups, then what we see is that this picture is exactly the orbitals of this group action, the orbits on ordered pairs. So the orbits on ordered pairs is called the orbitals, and the orbitals of a permutation group action always form a coherent configuration. Now, this is the original root, actually, of the entire concept. So Schur gave this combinatorial model to study permutation groups. Take a permutation group and then look at the orbitals, and he noticed these axioms, the axioms that I just described. So he was looking at a symmetrical structure, abstracted some regularity conditions out of that, and postulated them, and then did not study them, except in the case of a permutation group, in the symmetrical case. But then the same concept then arose out of different contexts. For instance, for Weisfeiler-Leman, it came out of the consideration of the isomorphism, graph isomorphism and graph canonization problem, where already, I mean, they gave the exact same definition. However, there already the typical examples were not symmetrical. Okay, so most coherent configurations are not Schurian. They don't come from permutation groups. Okay, so now coherent configuration is homogeneous if every point, every vertex has the same color, and it is primitive if, in addition, every color constituent other than the diagonal is connected. So, for instance, in this picture, there are 2 off-diagonal colors. So there are 3 colors altogether. One is the diagonal, the black, and then the red is an off-diagonal color, and the blue is an off-diagonal color, and each of these is connected. We call this configuration primitive. Whereas here, if you look at the green off-diagonal component, that's connected, but the 2 other off-diagonal components, the blue and the red, are disconnected. Therefore, this configuration is called imprimitive. So this is a critical distinction. In a way, the primitive coherent configurations, they are sort of the atoms. They are the indivisible objects in this study, and that also has algorithmic significance. When we don't have, well, we want to use some sort of divide and conquer, and these are the ones that don't offer an immediate, obvious way of dividing them. Okay, so now let's look at the Schurian case. So when this comes from a permutation group, well, if it comes from a permutation group, then that permutation group is going to be transitive if and only if all the vertices have the same color. I call that homogeneous. And that permutation group is primitive. Primitive means it doesn't have an invariant a non-trivial invariant partition. That's equivalent exactly to the orbital configuration being primitive, in the sense that all the orbital graphs are connected. In one direction, this is trivial. If an orbital graph is disconnected, then those are going to be, actually, the connected components of that are going to be domains of imprimitivity. That represents an invariant partition. Okay, so so I looked at this 35 years ago and found that primitive coherent configurations, the non-trivial ones, okay, I say rank at least 3. Well, what are the rank 2 configurations? Diagonal and off-diagonal. So that's called a clique. So the clique configuration, of course, has n factorial automorphisms. But all the other primitive coherent configurations, so the non-clique primitive coherent configuration, have substantially smaller number of automorphisms, exponentially in square root of n at most. And this bound is tight because we saw strongly regular graphs are primitive coherent configurations if they are not non-trivial, and some of them have actually this number of automorphisms. So this is a tight result. One of the reasons why this paper was of interest is that it solved a then 150-year-old problem in permutation groups, namely bounding the order of primitive permutation groups. So this, even though this was purely combinatorial, and I couldn't even use any graph theory in it because group theory in it because there are no groups here. Nevertheless, it solved a problem in permutation groups that was not previously solved. So now the O tilde notation, okay, the big O notation hides a constant factor. The O tilde notation hides a polylogarithmic factor. That's a standard convention that is started from theoretical computer science, but it is spreading now. Now, a tournament is an oriented complete graph. So every edge gets an orientation. If the tournament itself happens to be strongly regular in the same sense as the graph, then that has a quasi-polynomial number of automorphisms. Okay, so here is the result, and we know that this is tight, apart from whatever logarithms are hidden in the tilde. So the challenge was to reduce this bound with known exceptions. We know the exceptions. The exceptions are the Hamming graph with parameter 2 and the Johnson graph with parameter 2 and their complements. So with these exceptions, we have to reduce for the rest. And that challenge was waiting for somebody to solve it for more than a third of a century. So my students, John Wilmes and Shaori Sun, who was a student at Columbia University, they reduced the exponent to 1/3. And here, again, you have to realize the fact, I mean, proving something for all objects in a class may be hard or maybe not so hard, but proving something with exceptions adds to the intellectual challenge. Very clearly, we need to build a big gap between the exceptions and everything else. And so they developed an entire structure theory of primitive coherent configurations. There was simply no combinatorial structure theory before, not even for very special cases, except for strongly regular graphs. Strongly regular graphs are a very special case of primitive coherent configurations, and for them, Neumeier in 1980 produced an amazing structure theory that in particular involves the notion of clique geometry. So what this means is we look at cliques, and the cliques somehow behave something like a Steiner design. Basically, what happens is that through every pair of points, there is at most one. In fact, what happens is that for every edge, there is exactly one large clique that contains that. And that kind of clique geometry and the intuition, geometric intuition that comes with it is helpful. In particular, the exceptions have that clique geometry structure. So I'm not saying that the clique geometry structure is present for every primitive coherent configuration. It is present in some range of the parameters, but there are so many parameters that even to cut order among these parameters, that's itself a difficult task. And then defining what cliques are when we have such multiple colors. Those cliques are not cliques in one color. Those cliques are unions of colors. And so, among other things, this clique geometry achieves separation of the exceptions. All the exceptions have the clique geometry. Okay, so this is a very interesting paper, and I hope that somebody will pick up the task and tries to go further. We know what the exceptions should be, okay, conjecturally. So, but however, the structure theory goes this far. That's what we get. Okay, how do we know the exceptions? Okay, we know it from the symmetry. So here the belief is that unless the automorphism group is very small, all the rest is not just primitive in the combinatorial sense, but it actually has a primitive automorphism group which is very large. So, and large primitive permutation groups were characterized by Peter Cameron in 1981 under the assumption of the classification of finite simple groups. And the result was actually even stronger than what I am stating, because he went all the way down to n to the log n, but I am only interested in a threshold of n to the log n, and so here is the characterization of those that are not greater than n to the log n. So the exceptions, all of them have a unique minimal normal subgroup, and that subgroup, which is called the socle, so the socle is the product of minimal normal subgroups, but if there is only one, then that is that minimal normal subgroup. The socle is a direct product of alternating groups, and they act in a naturally induced action on a set of this size. So what is the naturally induced action of a product of R copies of the alternating group on a set of this size? Well, on each copy, we have the induced action on the Johnson scheme, and then we act on these copies separately as if that was a Hamming scheme. So what we get is actually, it is going to be a coherent configuration which is a hybrid between the Johnson and the Hamming schemes. It is and I call it Cameron schemes. So we know exactly what these Cameron schemes look like, and what Cameron proved is that if a primitive permutation group is large, greater than n to the log n, then it actually acts on one of these, and even acts rather fully. So at the minimum, these alternating groups are there. The top, that could be permuted by the symmetric group, or something less, it could be permuted. The copies can be permuted by any transitive permutation group. Okay, so the task is, the ultimate goal is find a combinatorial relaxation of this result. So we do not assume symmetry, we only assume regularity, and nevertheless conclude that the groups have small order, maybe not this small, but some small. I propose quasi-polynomial as a rather ultimate goal with known exceptions, but the known exceptions are exactly those that Cameron listed, so all the exceptions would be not only regular but symmetrical. Okay, so this is the conjecture that I like to propose. If you have a primitive coherent configuration that is not a Cameron scheme, then the automorphism group is quasi-polynomially bounded. And more than that, I'd like to propose that this result be effective. So it is not just that somehow magically there is a bound on the number of automorphisms, but this bound can be found by individualizing a polylogarithmic number of points, which will be followed by an efficient canonical refinement to complete split. So a polylogarithmic number of individualizations will split the entire structure. Split means that after refinement, every point gets its own individual separate color. If that could be proved, then part A immediately follows. So that would be, part A is an immediate consequence of part B. Even strike out the word efficient. Any canonical refinement would already prove part A. Okay, but my hope is that actually the refinement itself is not going to be much more complicated than Weisfeiler-Leman. Now, this conjecture was confirmed with square root of n instead of quasi-polynomial, the number of individualizations. That's where I started, and now Sun and Wilmes confirmed it with n to the 1/3 number of individualizations, and of course, so here is the target. So that's the number that needs to go down. Okay, breaking symmetry. I'm using this term breaking symmetry because somehow I never heard anybody, or especially physicists, say breaking regularity, but I should be talking about breaking regularity. That's what we need to do. We need to break regularity. We have a configuration that is regular. We don't know what to do with it. The vertices may not be equivalent under automorphisms, but nevertheless, they look all the same. How can I break this regularity? Okay? So this question comes, the question that I'm going to discuss here comes from a quasi-polynomial time, from this quasi-polynomial time algorithm for graph isomorphism that I have been working on. And the title of the section, so I am getting to the last question now among the 4 questions that I listed, is hidden irregularity. Okay, so how is this irregularity hidden? The graph may look very regular, but a small number of individualizations already destroys that regularity. Okay, so that's what I mean by hidden irregularity. So for instance, if you have just a cycle, imagine the cycle is, well, what could be more regular than a cycle? It's a beautiful regular object. But if I individualize one vertex, then already what happens is that I already get pairs. Every color class drops down to pairs, and then if I further okay, if I individualize one more point in addition, okay, say this, then all the regularity disappears. Then everything all the regularity is destroyed, every point gets its individual color. So even though this looks like a very regular object, it has this very strong hidden irregularity. At very low cost, I can completely separate everything. Well, that's more than what I would actually be asking for. So I am thinking in terms of a recursive procedure where I don't want to necessarily separate individually every vertex. All I want to do is divide and conquer means that I want to split my set, not entirely unevenly. Say 10%, 90%. I'm happy with that. Okay? So if I can fix a fraction that the smaller part is not smaller than that fraction, then we can hopefully do divide and conquer. So, okay, and the target number of individualizations is polylogarithmic. So the question is, can I get, by a polylog number of individualizations, a good canonical coloring? That's one of the signs of not being so regular, that I have at least two colors, and none of them is dominant, okay? So a dominant color, I call a color dominant if 90% of my vertices are colored by that color. And that I don't like if there is a dominant color. So a good coloring is a coloring that has no dominant color. Now, but what do I do if I have a dominant color? If I do have a dominant color, I am looking at an equipartition of that dominant color class. So I want to partition it into equal parts non-trivially, okay? So the blocks of that partition should not be singletons and not the entire thing together. A non-trivial partition of the dominant color class, okay? Into equal blocks. That's what equipartition is. And I want this to be canonical, and I have been using this term canonical and never quite explained it. But what canonical means, for instance, a canonical coloring is a functor from the category of isomorphisms of graphs to the isomorphisms of colored sets. That's what canonical means. So what this means is that any isomorphism between graphs induces an isomorphism between the colorings that I produce from those graphs. Okay? So what we are doing here is not just assigning coloring to graph, but we are also assigning what happens with morphisms. The morphisms are isomorphisms, which is a trivial kind of category. So I'm not using, okay, then it's a misunderstanding. People said, oh, and you are using category theory. No, I'm sorry. I'm not going to please anybody who loves category theory too much. I'm using the language of categories. It is just like using the notion of Cartesian product. So this is the convenient language to express what I mean by canonicity. So now not only a coloring can be canonical, a partition can be canonical. In this case, I look at the category of all possible partitions. Or anything else could be. I could assign, so I can canonically construct something. And that will be the main point here. I have maybe a graph, and somehow I notice that inside the structure of that graph, there is another graph hidden somewhere, but canonically, so that if I take any isomorphism of my graphs, then this canonical structure that I found in it is also isomorphically mapped into the corresponding structure in the other one. Okay? All right. So, okay. So here is a regular graph. I start from a regular graph, a non-trivial regular graph. Can I somehow, at a low cost, in terms of the number of individualizations, can I achieve a good partition? A good coloring or a good equipartition, if there is no good coloring that I could do? Well, here I can notice, for instance, that these four vertices do not belong to any triangle, but all the others do belong to triangles. Okay? Oops. Ooh, this is not visible. Okay, I don't know if you see, but this became now light green there. Oh my, and this became a different color. No, this is invisible, I am sorry. So anyway, what I did was I separated these four vertices from the rest by an invariant, whatever invariant I can notice. And so that's a pretty good partition already. It is basically 2 to 1, so I am happy with that. Of course, one can go further and see that, for instance, this part is going to have an edge that is a bridge. Okay, if I remove it, it becomes disconnected. This part doesn't have one. So I can distinguish these by all sorts of invariants further, but I don't even care. The only thing I care for is that at least I find some invariant by which I can just split it into, say, 2 to 1 or 1 to 9. Okay? All right. So the question is, if I have a non-trivial regular graph, can I always find one of these? And the answer is no. The answer is no, and the Johnson graphs are the obstacle. Johnson graphs are tremendously resilient to good partitioning. So let's review what's a Johnson graph again. It has k choose t vertices, where k is greater than or equal to twice t plus 1. So the vertices are naturally labeled by t subsets of a set of size k, and two of them are adjacent if they differ minimally, if their labels differ minimally. And what one can prove, and this is not very difficult to prove, is that the multiplicative cost of any good coloring or partition would be exponential in k over t. Now, t can be small. T equal 2 is an important special case. If t is equal to 2, then basically k is about the square root of the number of vertices. So we have square root in the exponent, and that is the square root. Graph isomorphism for 33 years stood at exponential in square root of n. This is one major bottleneck that caused it, that was immovable. And so we should not underestimate what this means here. So think of the case t equal to, then this is exponential in square root of n. That's absolutely unaffordable. We cannot pay that kind of multiplicative cost. So in this sense, the symmetry of the Johnson graph is totally, absolutely indestructible. Okay? If we are not willing to pay an exponential cost, then what is going to happen is, if we individualize, say, fewer than k over t, right? Fewer than this, considerably fewer, say little o, I mean divided by log star n or something. So fewer than this number of vertices, then all is going to happen is that, all right, there will be some things that get colors, and there will be a huge residual Johnson graph that remains intact. That's all that is going to happen. So Johnson graph, you just hit it here and there, and then still there is a Johnson graph, just a little bit smaller. And it is embedded in such a way that all the symmetries of that Johnson graph are continue to be present. So the entire symmetry group that in its induced action. So the Johnson graphs are a disaster to this project. Except the silver lining is that only the Johnson graphs are so resilient. So what we can have is, instead of having 2 targets, we have 3 targets. The 2 targets are as before, either a good canonical coloring or a good canonical equipartition. So again, good coloring means no color class is greater than 90%, no dominant color. Good equipartition means we have a dominant color, and that color class we partition non-trivially. Or else, there is a canonically embedded Johnson graph on at least 90%. So, yes?
So there are these also variants of Johnson graphs with subspaces instead of sets?
No. Here it is Johnson graph, okay? No, with subspaces, so if I look at a vector space, then it doesn't have more than n to the log n automorphisms, the entire vector space. So if I am already there, then I am so happy. That can be attacked sometime in the distant future. But right now, we are only getting the combinatorial thing where it can go to exponential. Yes. So, okay, once again, canonicity is a functor. In particular, what it means that the Johnson graph is canonically embedded means that we discovered this Johnson graph in such a manner that we also recognize that any isomorphism between our graphs will result in isomorphisms of these embedded Johnson graphs. Okay. It turns out that for the purposes of recurrence that is being used in the graph isomorphism algorithm, this is sufficient. In fact, the canonically embedded Johnson graph reduces the potential number of automorphisms so tremendously, it is even much better than the others. If I have a coloring, I have a coloring which is ideal, say 1/2, 1/2, so half of them is red, half of them is blue, then the n factorial potential isomorphisms went down to n over half factorial squared. Well, that's an exponential reduction, but still. But what is achieved by the Johnson graph is that n is equal to k choose 2, and the n factorial potential permutations went down to simply k factorial. So that is k is only square root, roughly square root of n, Well, okay, square root of 2n. So what this means is that if I could repeat this, then I would be done in log n rounds, as opposed to log n rounds if I have just the constant factor reduction. So in fact, while Johnson graphs have really been major obstacle to progress for a long time, once we can find them, then they are our best friend. Okay, so what is hidden irregularity? Hidden irregularity is that at low cost, I can bring it to the fore. At low cost in terms of individualization, I can just display that irregularity. So what is the opposite of hidden irregularity? One would think that it's hidden regularity, but instead it is hidden robust symmetry, indestructible symmetry, symmetry that we can't destroy at other than a prohibitive cost. So that maybe is sort of something going in the direction of okay, we get if we have some sort of regularity, which is just defined as the opposite of the hidden irregularity, then out of that, without any classification, we can infer that there is hidden a very strong kind of symmetry inside the structure. Okay, all right. So of course, I would love to see more explicit results of this type, but this is what we got. Okay, and I think this is the first of this type. In fact, what I said was that this is a result, the Splitter-Johnson is a result that is true for, say, regular graphs. I start from a non-trivial regular graph, so it's not a complete graph, not an empty graph. And then I can find either a good coloring or a good partition or a canonically embedded Johnson. But this is true in much greater generality. We can start from a k-ary relational structure, almost arbitrary k-ary relational structure for any small value of k, say polylogarithmic k, and we can get the same conclusion. Well, okay, I mean, you should be protesting this because obviously if the automorphism group of my k-ary relation structure is the entire symmetric group, then there is no way of getting any partition or anything, any irregularity in it at a low cost. In fact, this is also going to be true if the automorphism group is not the symmetric group, it acts as the symmetric group on a large fraction, say more than 90%. If it acts as a symmetric group on more than 90% of my structure, then I'm not going to get any of these consequences. So I have to assume that there is this symmetry defect of at least 10%. So what do I call symmetry defect? A subset, so that if I pointwise fix that subset, then on the rest, the action of the automorphism group will be the symmetric group. And I take the smallest such subset. So the size of the relative size of the smallest subset, of which if I fix pointwise, then on the rest I have complete symmetric group action, that's the symmetry defect. By the way, this is an easily computable quantity. Simply because I just have to test which transpositions are automorphisms. And then the largest connected component of what those transpositions form, that is going to be the symmetry, that is going to be this symmetric set of which the complement is the symmetry defect. Okay, so that's the only thing I have to assume. So this is now the extended Splitter-Johnson lemma. We have a k-ary relational structure where k is polylogarithmically bounded, and we are assuming that it has a symmetry defect of at least 10%. So less than the symmetric group cannot act on more than 90% of this structure. This seems like a very modest assumption, and definitely it is necessary for any of the conclusions to be drawn. But then under this condition, we can already find one of the three things that I previously said we can find starting from a regular graph. So there is no assumption needed other than the symmetry defect on this entire structure. Okay. All right. So let me list some of the open problems that I have mentioned. So first of all, I'd like to see more and better types of examples of that kind of inference, regularity, somehow inferring symmetry from regularity without a chance of classifying all the objects that satisfy our regularity assumption. Okay, I would like to see asymmetric distance regular graphs of large diameter. So asymmetric means that it has no non-trivial automorphisms. One subject that I did not discuss, but it is also central to this new work on graph isomorphism is, okay, can we infer global symmetry out of local symmetry? So we observe that somehow locally our structure looks very symmetrical. Can we conclude that the entire structure is somehow symmetrical? So this is something to which in most contexts the answer is no. But I'd like to see reasonable contexts where the answer is yes. And I believe I know some. Okay. Now, a deeper structure theory of PCCs, of primitive coherent configurations. So the Sun-Wilmer structure theory is already quite deep, but we have to go deeper in order to break now the 1/n to the 1/3. And so that's the next goal, to try to prove that the automorphism group of the primitive coherent configurations is smaller than exponentially n to the 1/3, ultimately quasi-polynomially bounded with known exceptions. Okay? Or at least prove this thing for strongly regular graphs. So for strongly regular graphs, there are no exceptions other than the already known exceptions. At least no exceptions are expected other than the known exceptions. So for strongly regular, the threshold, the divide is extremely wide. There are those two kinds, the Hamming and Johnson kind, which has moderately exponential number of automorphisms, exponentially in square root of n, and only two types. And then everything else is likely to have no more than quasi-polynomial number of automorphisms. By the way, there is something in this direction that I can prove and I didn't talk about, and that is the following. Suppose we have a strongly regular graph, which is not one of these two exceptional kinds. What one can prove is that its automorphism group does not involve an alternating group of which the degree is more than log squared. In fact, even more than Constantine's log. So what we can prove is that with these two exceptions where huge alternating groups are involved in the automorphism group, all the other strongly regular graphs have only tiny alternating groups involved. And this is significant both in terms of characterizing what kind of groups they can be, but also from the algorithmic point of view. So the question is, this is proven by spectral arguments. I mean, there are two kinds of spectral arguments that go into this. One is that the regularity constraints imply a matrix equation on the adjacency matrix of our graph, and therefore they have very strong implications on the eigenvalues, the multiplicity. So there are a strongly regular graph has only essentially three eigenvalues. I mean, one is the degree, and all the other eigenvalues are only two kinds. And one can also infer the multiplicity of those. And so there is spectral theory here. In particular, we can also estimate the spectral gap, and then we can use another kind of spectral argument called the expander mixing lemma. So that somehow tells us that graphs where the eigenvalue gap are large behave in a pseudo-random manner. And the combination of those two types of spectral arguments then gives this result. However, this kind of argument is not available for primitive coherent configurations in general. So I don't know what method could work to generalize this method to primitive coherent configurations. There is a representation theory of primitive coherent configurations, and maybe that's the analog of spectral arguments, but I'd like to see something work on that. Okay, and then just one last question that I'd like to mention is, can we prove that the automorphism group of a projective plane is polynomially bounded order? Okay, so thank you. I'm sorry, what are the implications of what? Okay, so so the question was, what are the implications of the rank of a coherent configuration? So if the coherent configuration has rank 2, then it's a clique, so that's trivial. If the rank is 3, then it is either a strongly regular graph or a strongly regular tournament. So it means a strongly regular orientation of the complete graph. And so there is very substantial work that has been done on this, and in particular, we know something even in this specific context about those. Even if the rank is bounded, then we know something. And one of the difficulties that Sun and Wilmers had to overcome was that they lost a logarithmic factor in the exponent. It's not significant particularly, but surprising nevertheless, because of the possibility of unbounded rank. So for bounded rank, somehow their argument would be somewhat easier. So the structure theory becomes more complicated if we are not bounding the rank. So that's at least one implication of the rank. The rank is also, okay, so it corresponds to the number of constituent colors which correspond to the number of generators of the adjacency algebra. So we are also talking about the dimension of the adjacency algebra. Yes?
Yeah, your third open question looks to me like something one might somehow think about for posets also. Have you ever thought about anything for...
Oh, posets are isomorphism complete, so it would be equivalent. Okay. You can think of any class of structures that is isomorphism complete, so that means that graph isomorphism can be reduced to it, and then the same question stands. Okay? But I would be interested also in smaller classes, so that's a very broad class. But I would be interested in more restricted classes. So for instance, for strongly regular graphs, one can prove, well, we cannot prove that strongly regular graphs are not isomorphism complete, because in order to prove that, first we would have to prove that P is not equal to NP. But all known proofs of isomorphism completeness are actually functorial. Okay? And it is easy to prove, well, not easy to prove, but it is based on that result that I just mentioned. One can prove that strongly regular graphs are not isomorphism complete through functorial reduction. Okay? So at least this is a somewhat more limited class. But it would be interesting to look at trivalent graphs, for instance, also, which are absolutely, I mean, seemingly much simpler case for this, because their automorphism groups are so much more restricted. The stabilizer of an edge is a two group, so that has a very restricted structure.